Welcome to Industrial PLC Applications. This video is on planning the control concept to sequential action. In instrumentation and process control, you learn to take the forces of nature, pressure, temperature, fluid flow, and fluid level, and convert them into a usable signal. In Level 1 PLCs, you learned how to form ladder logic by placing a few instructions on a rung or two and having the PLC execute those rungs to perform a simple task. This next level will assist you in analyzing a desired final process and create the necessary logic to make a sequence of events that run an automated process. After working through this course, you'll be able to analyze a task as requested by a customer, break down the request into a sequence of events, then using the skills and instructions already developed from Level 1, write the necessary ladder logic that successfully accomplished the task as requested. The first thing we do is we break everything down into the basic physical requirements and limitations. What do we need in the way of material? What specifications and regulations are involved? What kind of programming is required, and who will do the programming? The next part is figuring out the basic properties and parameters involved. So, for example, where is the program going to be working? What inputs and outputs do we have to monitor and control? What are the timing sequences or accounting registers that we are dealing with? And what are their ranges, their time base, their minimum and maximum? All of these things have to start entering into our bigger plan. Finally, we get to what is the functionality of the program? What is the process supposed to do? What is the order of operation? Then what initiates the process? What can stop the process unexpectedly? In other words, safety. What stops the process naturally? In other words, when is the system done or the current cycle complete? This is often how a project is explained, not how you program it. Before delving in too deeply, let's take a step back and examine something we might do for ourselves on any given weekend, like building a garden shed. Before you can do a thing, you need a lot of preparation. So, what do you need? When going through this thought process, the first thing that should come to mind is sometimes it's a lot better to ask first. For starters, do you know what you want? Do you have a plan? Will you be allowed to build the shed? Or will you have a freshly minted enemy next door when you're done? Without this asking first mentality, you could end up being in a situation that you're not really planning for. For example, maybe your neighbor that you didn't talk to decides it's on his side of the property line. Oops. So now you're fighting a lawsuit. Maybe the city doesn't allow for sheds. Fighting City Hall is time consuming and costly, especially if fines start to mount. Clearly, ask first, avoid lawyers later. To avoid all this, you should create a checklist and a plan. In programming, we call this combination of checklist and plan a requirements analysis form. An RAF, or requirements analysis form, may sound intimidating or even boring, but it's not only a good idea, it's a professional thing to do. It's also a great time and money saver. We've seen how regulations can come into play, but what are some of the other requirements we need to think about and address? Getting back to our shed analogy, here are some questions, and there's always more questions to ask. Do you have a plan? How big is this shed? Is it wood or is it steel? Is it a custom built job or is it a kit? These decisions, once made, may not be reversible. So be careful what you decide. You're going to be stuck with the results. Once all of the decisions are made, you can then generate a materials list And once this is accomplished, you can go out and purchase all of the materials. Your decision has brought about other ramifications. For example, the other thing your decision did was to determine the tools you will require. If it's wood, you'll need a hammer and a skill saw. If it's a kit, you'll need a screwdriver and wrenches or a cordless drill. Every decision came from a crafted question. We've got the broader scope, the big idea. We're going to focus on the RAF in another video series, get into it in a little bit deeper. For now, let's skip ahead somewhat and begin to think about our program, the logic we will be writing. There is a logical approach to building a PLC sequencing program, just like building a shed. In level 1, we talked about the ABCs of PLC ladder logic. Let's revisit that. Every rung of logic can be broken down and thought of as 3 distinct sections or components. The ABCs, the absolutes, the business, and the conclusion, or consequences, and a new letter. The A, B, C, and D's of ladder logic. Here the new letter is D for details. During your planning stage, you may find certain things that do not fit neatly into a box, or more ironically, are only in a box. These are things like timers and counters and internal variables that will be used like an output. While they're fresh in your mind, create them in the global or local variable collection. It's easier to do it now while it's in front of you as opposed to later as to what is that DI00 thing again? Now here's the part that's going to throw you, because we're going to jump to the C of our logic. When you began your shed, you likely had a vision of the shed in your head. Ladder logic programming, especially sequencing, always starts with the intended actions you want to happen. It also means considering what consequences could happen if things go wrong and finding ways to prevent problems and mitigate them in logic. I know this sounds an awful lot like putting the cart before the horse, but work with me for a minute. In level 1, you programmed a conveyor. The conclusion of anything you did was to have a motor start and stop when you directed it to do so through logic. As the system developed, it was necessary to make changes to arrive at different conclusions, like a timer to determine if a parcel did not arrive due to unforeseen circumstances or consequences. But over time, the conveyor was only one of many outputs. You had pilot lights, a warning horn, a sorting pusher, a second conveyor permissive, and there could have been even more if you wanted greater sophistication in the system. All of them always begin by what do you want it to do? Sticking with the letter C, create a concrete plan. Before you write a single rung of ladder logic, write down what it's supposed to turn on or off, and the order of operations. Imagine starting a game of hockey by blowing the whistle, skating fast, and swinging a stick around, only nothing happens. Nothing works if the puck hasn't been dropped to the ice first. So let's organize a little bit more. Just remember that preparation is inversely proportional to failure, while failure is the square of unpreparedness. So let's create our own Golden 8 checklist. It's a great way to organize your thinking and your programming. So first of all, number 1, what will stop the program? Notice I didn't say how to start. Doesn't matter if you can get it to go, you want to be able to make it stop. Number 2, define the most important outputs and program them first. Number 3, define the bells and whistles. Program them second or third or maybe last. These are things that you want, but aren't necessarily going to stop the system. Number 4, define the restrictives and limitations. Restrictives are things that will prevent you from running or stop the process when it's supposed to. Limitations are things like timers. How long do you have to get something to work? Or a counter. How many are we making before we have to stop? Number 5, define the permissives. Now with permissives, they are also real world and internal ones. So define which ones are giving permission for the cycle to work. Number 6, look for alternative ways to energize and maintain, which is a parallel type of logic, or defeat, a series logic that will operate an output. Number 7, write a rung the logic, observe the flow. I cannot stress number 7 enough. If you do that, you will catch your errors. If you don't do that and you wait till you're completely finished, you may spend more time troubleshooting than it's worth. Number 8, check off each output you have made operational. This way you keep track of how much more you have to get and when you're finished. Once you've sorted all this out, you can start thinking about doing your programming. Now, personally, I don't like people to do their programming right away. They'll stumble along, but they won't listen to whirl. So for those who are code first, solve logic later kind of programming, I get it. You'll get the job done. Let's compromise here though, and make your life a little easier at the same time so you won't forget something. Because I find that when people just rush in, they inevitably do not get all of the outputs energizing. They get fixed into a problem and things are dropped. So I'm going to show you a way to fix that. The first thing I want you to do is to create a dint and call it step. Then write the following single rung of logic and copy it as many times as you have identified outputs. For each new output, change the active component of the dint structure. For example, step.1, step.2, step.3, etc. While doing this, you can even set up branched outputs at this time if you want. You can deal with the complexities and details, in other words, the business section details that we'll be covering shortly, as you discover them during your programming, and backfill when and where you are necessary. Of course, if you look at the logic, none of the rungs will work because step 0 cannot be true and false at the same time. And if it could, the opposite state would cancel it out. Anyway, you can then backfill the logic as you develop it. At least you should have every conclusive outcome listed and not missed. For those who have already typed in the aliases in the global or local variable collections, you can create the same rungs of logic, but use your newly minted or input or output variables. Once this has been accomplished, we can move on to section A. For the rest of us mere PLC mortals, this is the time to revert back to D and begin to type the aliases for any and all known variables you have listed in the properties and parameters section of the RAF. You can go see the RAF video for details if need be. Every input, output, or internal variable should be entered in the variable collections first. It will save you time and keep you focused on the logic, not the nomenclature. Why try to keep inputs and outputs swimming around in your head? Let the software free up some gray matter. One and done. Right, so you've been itching to write your logic. Great. Now we can go and start looking at our ladder logic and organizing our inputs, outputs, and instructions in the correct order. And we now go to the A section, our absolutes. These are things that each rung must have before the rung will work. We put these as close to the left rail so that when the machine stops, they are seen first and can quickly solved or ruled out. Remember whirl, write a rung, run the logic. And in this particular example, it caught the very first error shown. Keep in mind that sometimes programmers use implicit absolutes, variables that are understood to be absolute or are controlled by a rung with an absolute. For example, the MCR contact shown has a stop push button that will disable the MCR output coil in rung 1. And therefore, this rung 2 contact will also be disabled. However, it's not considered bad form to repeat the underlying logic. And in some cases, it can really help, especially if it is a long program. One overlooked absolute is the not option of the opposite selection. I know that sounds kind of confusing. Let me explain. In the rung shown, the motor cannot go forward if the motor is running in reverse. These are called interlocks. They can be simple as shown or can be complex. Think, there should be absolutely no way that can happen. The B section will keep you busy. You will often start with a simple rung and keep embellishing it and honing it until the program performs as desired. The bulk of your time will be debugging, rebuilding, bartering position, and basically building the rung Lego block by Lego block as new options for running are desired or discovered. As you add branches and alternative programming, you will be thanking me. I strongly recommended doing the aliases first. And if you whirl, you will be able to troubleshoot each rung as you go, as opposed to sifting through 50 rungs of logic, all because of a mistyped variable. And at last, but not least, we return back to our D, this time for documentation. Always remember this. Professional electricians who document properly aren't making themselves disposable. They are proving they are indispensable.